Right, so I'm going to do some more testing on this Fluke. Let's get this microphone in the right place so you can hear me a bit better. And without blocking the view of the meter would be quite good too. Okay, sorry for that. Now, I've got this extended card working. I think I might have solved the problems with it shorting out the power supply. I'll scrape between all the tracks and stuff. Anyway, that's a different thing. So, I think it's okay now. I'm not 100% certain. I don't trust it. But what I've got here is the oscilloscope hooked up to the oscillator assembly board. This is on its output connection, and I've got the Siglent 6.5 digit meter hooked up to the output. Now, what I should see from this test point here is a voltage and a frequency. Right, so you should see the oscillation working, and I should be able to see the oscillation changing depending on what frequency range you've got set and what voltages you've got set and stuff like that as well. So that's what you should see on the scope over there. Spin this around a bit. Okay, so that's the plan. Now you can see the trace there just in the background. I've got a scope set to 1 volt division, so it should actually up to 4 divisions is what should come out of that. Let's turn on. Unfortunately, it's still a bit noisy because of the fan. Really should do something better, like unplug it. I don't know. Anyway, so what? Got to wait for it to do that warm up period of 30 seconds. So I've still got 1 volt output, 1K frequency, the 1 internal sensing, phase lock off, local control. It's got the links on the outputs between the sensing and the output terminal. It's all there. Okay, right. Operate mode. Nothing on the output. Is it's on DC, not AC? Is the reason for that. Effectively, I'll stick it on dual meters, but you probably won't be able to see the second one. So, yeah, it's like 22 millivolts coming out. Okay, AC, and nothing on the trace. So if I change frequencies, still nothing. Nothing showing up on the scope at all. Change voltages. And nothing showing up on the output still. Right, so no change there. Right. But when I go to 100 volt range, look what happens. I'll get 161, well, negative 161 volts DC on the output, which is interesting. Right, if I do the 10 volt range, I'm getting 8.9 volts DC on the output. Well, minus 8.9 volts. We're at 4.9 volts, 4.9 millivolts, sorry. Right, AC. And on a 100 volt range, I'm getting 7 volts. Oh, sorry, 7 millivolts AC. Right, so there's some voltage leaking through from that power supply board or power amplifier board. 1,000 volts obviously doesn't work, so I've got the other unit. Right, so that's given me a clue at least. Actually, I should do something else. So that's on the output of the oscillator. There's nothing there. Oscillator output just doesn't work. So it's got various stages in the oscillator, and I just need to find the circuit diagram for it again. Remember which stage I'm supposed to be looking at now. There we go, next page. Right. So I now need to connect to somewhere else, which is let's say that's test point 7. If I go to test point 4, is it? Hold on, try and see. Had to excuse the top of my head. Test point 5, there should be a signal there. At an earlier stage. and again there's still nothing there. And if I go to test point 3, there should be a signal there, also at an earlier stage, and test point 3 is here. Still nothing there. So the oscillator board isn't oscillating, which is why nothing else is working, because it needs this to work. Okay, so now the oscillator is like a loop system. It's like a closed loop. I'll go on the computer in a second and explain it, as well as I understand it anyway. And yeah, but because it's got each discrete stage, and then that loops back to itself, and that's what forms the oscillation. So anything within the whole unit, within this whole card, can cause it to stop working. So it's in here somewhere. Right, so I've got to show you the voltage measurements on this board, just to prove there are voltages here. So over here is markings on the board. So we've got plus 15 volts right there, correct. Minus 15 volts, correct. Minus 30 volts, correct. I'm not sure what the other ones are. Probably nothing. Right, so those voltages all seem to be as they should be. At least on those marked test points there. So yeah, why it doesn't work, I don't know. Not yet anyway, we'll get there. Alright, so this is the circuit diagram, well, the block diagram for the unit, just a simplified version obviously, and just trying to explain where we are in the diagram and what I've found. So I've looked at the oscillator here and found there's nothing coming out here going to the power amplifier. Alright, so that's one fault. The second fault is that the power amplifier here, the output coming onto the output terminals, has that minus 163 volt DC output. It's supposed to be a 0 volt DC output. It's supposed to be balanced, which means the positive supply is not pulling it central. Alright, so there's an issue with the power amplifier output, and there's an issue with the oscillator output. Now the question is, because this is a closed loop system, what's causing the oscillator to fail? Now, what I've got to check is the frequency control from the front panel to make sure it's actually trying to set the oscillator to the correct frequency, because if that is faulty, then the oscillator may not run. The other thing here is the amplitude control coming from the oscillator control assembly. If that is faulty, it may mean the levels are so low it's not running. I'm less suspicious about that signal as I am about this one, or possibly just a fault on the board itself. Now the other thing I need to check for, because it looks like a good starting point to be honest, is the reference assembly here. So it's got the amplitude selections going to reference assembly, which then feed into the AC/DC converter, which is part of the closed loop correction system, right? So this amplifier detects the input from here versus the reference input and produces a correction voltage, right? So so that is all part of that as well. But because that is like a standalone point, that's a good thing to check, because I can actually verify the reference is working and eliminate this as a fault. And it could well be faulty, I don't know. I'm suspicious that every single board in this unit is faulty, to be honest. So it's going to be a long repair, as is already evidenced by this being video number 8. So I'm sort of torn between jumping back to the reference and verifying this just to eliminate that completely and move on, or working on the oscillator section. No point working on the amplifier yet, because until I've got something here, what I'm getting out of the amplifier may be wrong anyway. So once I get an oscillator working, then I can verify the amplifier. Now an option I do have is to actually inject a signal into the amplifier and see what happens. You know, I could inject my own oscillator signal into that within the selected ranges. Let's just scroll down to this section here. Let's just make it a bit bigger so you can see it a bit easier. Right, so the oscillator section Double integrator type RC oscillator containing oscillator assembly, right? So yeah, it uses resistors and frequency selection capacitors in order to adjust the frequency. It uses phase shifts. So it does phase shift 90 degrees, and then another 180 degrees, and then it does another phase shift, another 180 degrees, to try and get 360 degrees of phase shift. Obviously, I'm skipping over here. You can read it yourself. Which means when you get 360 degrees, you get an oscillation. It will feed back, and it's got a fine-tune control, which it needs only the parallel electronically controlled feedback paths in the oscillator control PCB, which is why that's also important, to bring the combined loop phase shifts to exactly 360 degrees, and thus sustain the oscillation at design at the selected frequency, which means it relies on us phase shifts working in order to oscillate. It also relies on the feedback from the oscillator control PCB to oscillate it correctly, because that's that correction voltage for the oscillation, which tunes the frequencies. So that's why all of that is so important. And it's controlled by 12:1 range by selecting values of the selected frequency, select resistors, and the inputs in the quadrature and oscillator amplifier. So that's on that board. I'll jump to that diagram soon and show you that. And that's using FET switches to control all the switching for each resistor and capacitor. And I'll jump to the amplifier stage here because it's on the same page. Yeah, amplifier accepts 0.33 to 4 volts output from the oscillator. Right, so that's what I should be getting at the oscillator, is 0.33 to 4 volts. And then it amplifies up to between 1 and 120 volts. Right, has two gain settings, 3 and 30. So it's either doing 3 times that voltage or 30 times the voltage. Right, so which is where it gets 120 volts from that 4 volts range. So if I want to inject a signal into the amplifier to test its output, that's what I've got to do, is in that range there. So that's all, fairly simple. Because it's a closed loop system, I'm likely to have to jump into that loop and inject my own signals in order to test it. And test each part of it. I might be able to eliminate parts as being problems, for example, and simplify what I'm troubleshooting. What I'm looking for here, here we go, the mid-stage. Mid-stage of the amplifier drops the DC operating point of the amplified oscillator output to minus 190 volts DC and provides voltage gain, right, because it's amplifying the input voltage around that 190 volts. The upper stage operates in conjunction with bootstrap amplifier, produced a 1 to 120 volt output to the attenuator, so that's what I should be seeing at the output, is 1 to 120 volts of the amplifier, and I'm not getting that either. Not on all ranges. The function of the bootstrap amplifier is to eliminate the need to connect the output stage directly across the plus 190 and minus 190 volt regulated supplies by allowing the stage to float between these potentials. The low voltages produced by the Zener diodes provide the necessary collector voltages for the output transistors in place of the 190 volt supplies. So I've got to get my head around that part of it yet and how that works. But yeah, let's just try and find this other section. So I'm trying to think what I'm saying now. So the minus 190 volt issue there is interesting, because that means that the positive supply isn't being strapped. That should be balanced by the positive 190 volt supply. I'm going to diagrams now somewhere. Let's find the right one. And so that's obviously not happening because it's just getting the negative supply coming out. I just need to find the right diagram. The attenuator. I might have to come back in a second. Power amplifier, here we go. No need to come back. Wait for the thing to wake up. Right. Let's try and zoom this in. So also you may have noticed I've got that overload indicator on all ranges except the 100 volt range, which is where I've got that voltage coming out, so which is interesting. So that's the minus 190 volt regulated supply down here, and this is the plus 190 volt supply here. That's the output there. Let's go a little bit bigger again. Nice, that's the output there, and that's what I'm measuring at minus 163 volts, which is obviously biased from this side. So this side is working, that's pulling down. Either it's locked on or it's pulled down, but if it's locked on I'd see it all the time, so I'm thinking it's probably switching on. And the positive side isn't pulling it down, so I'm not quite sure the exact arrangement. There are relays in here. There's a relay here, K1, and I think there was another one. Oh, I don't see it right now. Pretty sure there's another one here somewhere. There we go, K2 over there. Right, so input comes in from an oscillator. It's got this detection in here for the limits and the overload and stuff like that, and that feeds through, and then it uses these positive negative amplifiers like this mid stage here, and then the to drive through and give the necessary signal. So there could be something here. There's current limiting stuff here, so I don't know. I've already checked every component on the board, well, all the transistors at least, and diodes, and the electrolytic capacitors. So I haven't actually found where it's wrong yet. But so until I get an oscillator signal coming in here, then I can't say for sure that it's working anywhere near correctly. This is all the limiting circuitry here, so the limit stays on. And that's 190 volt range when it turns off, which means the limit circuit is working to a form. When I'm doing that higher voltage, then it starts to work. So I need to probably do some more testing at the input stage to see what's going on there. So when you do a 100 volt range here, so there's a switching here, which turns on K1. So you do 100 volt range, that's an AND gate, so, oh, an AND gate, sorry. Oh yeah, because it's got plus 5 volts outside, so that's fine. So 100 volt range turns on K1 and K2. So when those are turning on, then I get an output. So that turns on K1 here, which feeds through from here, and K2, which is here, which feeds these two stages together. It links those two together, which is doing what? I'm not sure yet. Feeds this input here. Yeah, so maybe it's an issue with something here. Those are effectively parallel paths, so it could be something here is wrong. I should probably check these resistors. So yeah, I've got lots of options here to try and narrow it down. But so 100 volt range, it turns on, and the limit goes off. The overload indicator goes off. So this is a clue when that is switching that something in here is changing and starts to work, but the other ranges don't. And also that voltage offset, I've got to check everything in this side here to see what's going on there, because you know, I should be getting a balanced DC output. It should be 0 volts DC. It shouldn't be a massive minus 160 volts DC coming out of that thing. Right, so I'll waffle on enough about that. So the oscillator, which is a bit lower down, got to find it. That's the oscillator control. So that's the output of the oscillator control just here, which was one of them anyway. is all so it's all closed loop system. It all comes in and out of this thing, and it's got the phase locking there. Now this is one of the things we've got to look at is this bit here to check these inputs to make sure they make sense. So I'll make it a bit bigger so you can see what I'm talking about. Alright, so these are the inputs for the frequency selections. So I need to verify that these are all correct for the various frequency selections to make sure that they actually work. Alright, so I've got to basically measure these pins here. That's on a connector there, so I'll probably have to pull that board out and plug it on the header and see what's going on there on the extender. But I can measure those pins and see if these make sense against these, to at least verify the front panel controls sending the correct signals out to this encoder or decoder. And so that's one of the things I have to do. And I should probably verify these are switching as well. Let's remember how it works now, hold on. Yeah, so switching these various capacitors. Right, so I'll zoom in again. So these are the various capacitor assemblies on there. Now these have been played with on the board. I do remember seeing that these have been changed. So it's probably someone trying to troubleshoot it. Now if any of these relays had failed, that range would stop working. But none of the ranges work. So it's not just like one of these relays have failed, because they must have all failed if that's the case. So there's a few things I need to check on here, such as the voltages on this board itself, this quadrillary output to the rear panel. Now this I need to check. I suppose I could test there and see if that's changing anything there. I don't think it will, because it hasn't got any feedback anyway, so it's probably not pointless at this stage. But if I can just verify that this is switching, that would probably be something, and just see what's going on there. And the next thing I need to look at is zoom back out a little bit. Actually, let's look at the second stage here. So this is spread over 3 pages, right? So, so anything on here I can look at. Various drive signals here, which go through switching networks, and I think I did find a fault here somewhere originally. I think we're looking around here somewhere or something. And switch driver, so again you've got range changes here, so I should be able to measure on oscillation here. And switching at these circuitries here, so I've got some notes here which make it bigger so you can see it. It's got some notes here about timings and stuff like that on this gate. And this is zero crossing detector section, so oscillator should come in here, and this should be with the phase locking and stuff like that, should be controlling the circuitry. So I need to check all these voltages on the input of this as well, just to make sure all these are working, make sure we're getting there, because if any of these voltages are playing up, that also wouldn't work. Could be a, one of these diodes gone, or open resistor or something like that. It could easily be something like that. Right, and this page here is just drive circuitry pretty much. So it's switching this circuitry across there. It's also part of the oscillator circuit, so oscillator amplitude out. Right, so that's summing amplifier in and oscillator amplified out. So that's actually coming into the board, that's going out the board. So that's that part of the closed loop between the actual oscillator board, where it's comparing the levels. Alright, this is going on for ages, this video. Right. Now this is where I was looking before on the oscillator control board, on the oscillator board, sorry. So there's TP7 where I was testing, which is supposed to be a output, much like this. Okay, so, and then I went to TP5, which should give me this output, and I went to TP3, which should give me this output, and nada. Right, but again, it relies on being a closed loop system, so it goes, passes through. This is all the various switching circuitry for the various frequencies. So those are the FETs, and these are the controls. So the frequency control here switches these FETs on and off. Right, so it's obviously just the switching circuitry there. But you think if you're switching between any ranges, if there's one FET which is stuck on, it would, when you get to that range, it would still work. All right. Nothing obvious anyway, but I don't know. But, yeah, and it's got two sections depending on which frequency controls you're changing. So I should pass through from that stage through this stage here, which does a phase shift. It then passes through this stage here, which does another phase shift, and that feeds back. Where is the feedback? Is that the feedback there? Yeah, that's the feedback there. Right, feedback comes through here, I believe. Yeah, so you know, it's supposed to loop around, and then because it does a phase shift, it affects creates an oscillator effect. So each stage has to work. It's not like a single oscillator and then each amplifiers or whatever. It's actually the whole thing. So it's a bit more complicated than I'd like to do, because I have to check every single part. Because if one thing doesn't work, it doesn't work. And you can't say like test there and work out which stage isn't working, because the whole thing doesn't work. So it might be in a case of also just trying to scope each section at the time and try and determine what's going on as far as phase shifts. I might be able to see a pulse here, for example, and then see the offset pulse at the same time. It should offset, but I don't know. Anyway, I've got to figure out how I'm going to test this, but yeah, it's a bit tricky. Well, I'm just going to test this relay to see if I can determine if it's operating correctly or not. This one just here. So it's 1 megahertz dry, so when it's on 1 megahertz frequency, the relay is supposed to switch. It's got a diode in parallel with it, so I can get some sense out of that. Okay, so when it's not on 1 megahertz, that's powered. Okay. So let's see if I can make sense of because it's got two read relays that run through that coil. So that is powered now, so it should be connected together. Yep. Yep, seem to be. I'm not completely sure about that one switching properly. 2.5. That one's definitely switching. See that? Not convinced. I mean, something's happening. That side's rock solid. Could just be some residual stuff going on there, but yeah, that's it does appear to be switching. That's something, I suppose. Let's see if I can do this another way. Not sure what the other side is switching. I just want to see a more positive change. If I stick that on, say, there. Okay, it's 15 volts there. Nothing there. Okay, and then turn that off. 15 volts there. Yeah, okay, it's definitely switching. That relay's definitely right. So at least I know that's okay. That's one thing eliminated at least. there's still a lot of questions on this board about what is working. Part of the problem is that it's got that feedback, the quadrature amplifier out. Is that one? No, end. Quad amp in. Right, that's what I'm looking for. So it's just TP4, which is over here. Now, you probably can't see what I'm doing. Here we go. Right. So TP4 is just over here, and that voltage there is changing like a couple of millivolts, and that's based on the switching of all these transistors and FETs and stuff. So I'm thinking, well, that's not really changing, but that is also a feedback into the unit. So if I was quickly grab this diagram here, it's not as good as the one on the screen, but so TP4 is here, and it's all these FETs, and I was measuring the voltage here, and it's not really changing much. Though I can see some of these FETs are switching. I might have to do it in a logical way and actually check each individual one of them somehow. But this signal is required in order to change this part here. Right? This signal here should be changing or oscillating, and it's not. There's nothing going on. So if it's not getting past this point, it won't be able to get there. Now, that is based on all these FETs having a supply. So you've got the summing amplifier in coming in from over here, which runs over to it through a capacitor. We've got the feedback comes over into to it as well, and we've also got this relay here, which I'll just confirm is switching, and the quad ample in, right? So quadrature amplifier in is coming in. So that signal which should be feeding these FETs, which then gives a signal back to this. So if that signal there is missing, it may not be sufficient to actually turn this thing on, which could be part of the reason. Now that quadrature amplifier in comes from the oscillator control board, I think. I'll have to check that. So this just has raised more questions, really. So I don't know. I'm having trouble getting my head around this bloody thing. It's got so many interrelationships between the boards. It's not like one board just does this and then it goes to the next board and it goes to the next board, and it's like they all interlink, and if one part doesn't work, it affects the boards near it, not just that one. So it's a bit tricky to get your head around it all. At least I'm finding it anyway. But I'm going to work through it, and I'll probably do it via a process of elimination and just seeing which parts do work rather than which parts don't work. There's always two ways of doing it, you know. Sometimes you can find a part which isn't working, and sometimes you can find the parts which are working and do it backwards. And I think this is probably going to be a case of that, working out which parts are working and going from there. It's going to be fun. Alright, so what I'm going to do now is test each of the FET inputs to make sure they're switching. Now, these use a BCD based system. Right, so each one is a bit of BCD across each of the four frequency dials. Okay, so therefore there's 12 of them. I think 12. Something like, I think there's 12. Anyway, so these are all the FETs up here, and I'm pretty sure it's 12. Anyway, so this is the least significant, and it goes up. Right, so it should be 4 for the first digit, 4 for the next digit, 4 for the next digit, and then there's 4 more which I can't remember what they're for. Anyway, I have to look at the diagram. So if sorry, it's these ones here. Get the right row for a start. This row here is the FETs, and these are the switching transistors here. So those are just normal switching transistors for the inputs. These are the FETs it controls, and then there's a second set of FETs for the next stage. This is the stage I'm checking right now. It's this one. So if I go to the base, or the gate, whatever you want to call it, this one should change. I'm counting on 0. Go to 1. Yep, that's 1, 2, 3, 4, 5, 6, 7. That's as it should be. All right. That's all the way up. That's working fine. So I go to the next one. This should be on 2, 4, 2, 6 and 10. Alright, so that's 2, 3, 4, yep, for 2 bits. Yep, 2 bits. Yep, that's right. Okay, that one's correct. This is 4. So 1, 2, 3, 4, that's on. 4, that's off. Yep, that's correct as well. This one's 8. Yep, comes on 8. So 8 and 9. Yep, that's correct. Right, so those were right. So all these ones should be off currently. Just verify that. That one's on. Why is that one on? Because I'm not on 0. Maybe. I don't know. Which one's that? That is Q. That's 8-bit. That's actually marked on here too. I didn't notice that. So it's marked 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. It is actually marked on here. 1, 2, 4, 8. 1, 2. No, 1, 4, 4, 2. Interestingly, it's actually marked on there. It's convenient. Which one's that? It's on. Which one is on? That one is on, which is 8 with the second digit. That's interesting. So that one's actually showing us on. Anyway, we'll go through logically and carry on. So next digit is 0, 1, off, on, off, on, off, on, off, on. Yep, correct. Bit 2. So it's off, off, on, off, off, on, off, off. Correct. Digit 3. Off, 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 on, off, off. Yep, correct. 4. This one's on all the time. That's wrong. That should not be on all the time. But see, that's different part in there. Why is that different? That's interesting. So I'm going to have to go back and have a look at this and see what's going on here. One of these switches aren't working properly. Let's just have a look. Hold on. So actually I might just note this down, and so I'll do testing everything and I'll come back to it. So that is the 8th bit. 2, 3, 8, that one there, so that goes to K. Transistor K, it's marked, it's called FET K. So I'm going to put a little cross next to that one. It's okay, it's okay. Okay. Right, so that is actually being fed from Q10. Q10. Let's have a look at that. Q10. There's Q10. That is switching off. But the transistor isn't. It doesn't seem to be. What am I looking at here? Hold on a second. I shall come back once I get my head around it. Alright, I shall carry on with this, and actually I'm just going to move this. Actually it might not be safe. Hold on, right, I thought I'd put the book over the top of here and try and keep some of the noise down from the fan, hopefully. Right, so what I'm looking at now is that K, which is Q26. Let's verify that one again to make sure I've got the right one. Q26 here. Oh, it is turning on. Maybe it's not the right one I'm looking at. I'm looking at the wrong one. You only see millivolts there. It's only like 3.5 millivolts changing there. You're not really seeing much there, but it is showing switching. So this one here is showing as on the whole time, which is interesting. Maybe I need to be looking at the other side. Maybe I need to be looking at this side instead. Oh, there goes the book. That's a bit more obvious, isn't it? 15 volts to millivolts. I need to figure out which pin out this is. I know which one the common is. I'm going to have to come back to this one. Okay, I figured out what's going on there. Looking at the wrong pins on these bloody FETs. So I'm looking at this side, which isn't the right side. I should be looking at this side. So if I now look at that to bit 8, that's off. Then we'll go up to the on stage, it turns on. So that is switching. Right, so these are the input sides, but the output side is a little different. So if we go to the next digit, it's 1 on that one. That's switching. Right, so it is switching all the way up. Bit 2. Only thing I was checking for right now is the actual inputs to these things to make sure they are doing what they're supposed to do. Yeah. I think. Let's verify this one again. 2, 3. Yep, that's correct. 4. Yep, that's correct. So at least this verifies the frequency selection options go into this board, which means the front panel will probably be okay too. So that just verifies all that. Yep, that's correct. You've got the final digit here. Correct. Now you've got 1, 4, 4, 2, which seems kind of odd. So let's do 2. Okay, so I think one of them is probably mislabeled. Try that one's 4, shall we? No. That's 8. I think. Hold on. 7, 8, yep, 9, 10, 11, because it's got 3 positions there. So this one here should be 4. That's 4, yep. That's interesting. Gets to 4, that's on. So it should turn off again at 8, but it's not. I'm going to have to look into that. I know it's something a bit weird with that circuitry. Okay, yeah, that one there has got some circuitry which is different. It's got a diode bridging between parts, and there's also a link between the connections as well on the input side from the transistors over here. So we'll just have a little feel, see if it feels warm. Sometimes that's a clue. That's okay. That's a bit warm. That's a bit warm. That's much warmer than that one. And that one. This one's the hottest. For the same parts, I'd be suspicious about that part. Anyway, so far so good. The inputs to the FETs up to there looks correct. Now I was looking at the output before by mistake, so I shall carry on with that, because there was this one here which looks a bit strange. So should be bit 8. You can see it's jumping around a little bit there, which is a little interesting. But that's, you know, millivolts off and on, right? And that one's looking a little bit different. I'd like to know why that looks a bit different. This is next digit over. Maybe that's got the same deal. Yeah, it might, I mean, I'm measuring millivolts, so it could just be a little bit of circuit leakage in there. The other ones just don't have it. Yeah, it's not really showing up, so. It could be a just a reading error, I think. So I think these are all working okay. From what I can tell, it looks, it's probably right. Narrows it down a bit more, doesn't it? Well, what I've decided to do, I'm going to measure between two test points to check the switching of the FETs. Right. So I was looking at the circuit diagram, thinking, well, if I measure across the FETs, I can actually verify the FETs themselves are switching, and I know the inputs are there. So what I'm going to do is I measure between TP3 and TP4. That is measuring those resistance values, right? Because TP4 is on the input to the FETs. Gate joining source, whatever the hell it is, I don't know. Source. I'm not really up to speed with FETs. I'm not really good. Anyway, with the terminology I use transistors. Anyway, so if I'm measuring on this rail and on this rail, what I'll be measuring is the resistance values, depending on which FETs are turned on. So I should be able to actually see each step of a FET switching. So I've got it set up. I've got one clock clip on TP3. I'm just going to put no clock clip on TP4, just so I don't have to hold it. Should be okay, hopefully. Alright, so that's with the frequencies set at all zeros. Right, I'll set that on 100 Hz. Right, so I should be able to see the step each time I flick a switch. Let's just speed this up a little bit, shall I? Let's reduce the digits. Right, so 97, oh, that's switched. Right, so 95, 94, 93, 92, yeah, 91ish, yep. But it is switching, that's 881, 889, so they're different, that's fine. 87, right, so that's the first decimal. This is the tens digit. 8, 7, 6, 6, 7, 8. So as you can see, the number's changing each time, which means the FETs are switching. Let's look at the next one. Still a little bit close. That's right. So that one there's okay. So I went out to the thousandth digit. So this shows me that the FETs are all switching correctly. If I change ranges, it's not really changing much on those ranges because it's further on. So I'm confident now that all those FETs are switching correctly because the values and resistance values across those two test points change on each switching position. So I'm 100% sure those FETs are switching. Alright, so now I moved on to the next two test points, which is TP5 and TP6. So again I'm on the 100 Hertz range, and all the dials are set to 0. Well, apart from the first one, which is always 1. Now, let's do the same thing again, see if it changes. Yep. First dial is okay, second dial. That looks good too. The important thing as well is that it's not just changing, it's also not repeating the same number. Because if it does that, then there's a sort of effect which isn't switching. Yeah, that's alright. I was just flicking back and forwards there because I wasn't sure about the digits. That's okay. Next one. Yeah, that's all good. So, those look fine. Let's change ranges. Not sure, it does have some effect. I'm not quite sure exactly which way it goes. So that's 100 millivolts range, 1K range. That's when I go to 10K range, it jumps up. So I need to just see how that relates there, because it then jumps back down again for the 100K and 1 meg. So only the 10K has got a different value. Oh, see the scope? I've got a signal. That's why I left the scope connected up. I've got oscillation suddenly. Now that's interesting. That's with the scope connected. Maybe it's amplifying the scope oscillation. Do I have an output? Overload indicator still on. Let's just quickly plug something else in without disconnecting the scope. Hold on. And then I'll set probes. Oh, these ones. It's the first time I see any activity on the output, so it could just be that it's oscillating because of the multimeter being plugged in as well. AC volts. Actually, I might do dual. So, see it on there? There you go. So, let's see if I've got any output on this thing. Only on 100 volt range. Let's go through the dials, just in case something comes up. Not looking great, but okay. It's kind of what I expected though. Right. So it's going to stand. It's going to be a standby. Standby doesn't help, does it? Right. Sort of level then. As it switched between ranges, a sort of level. 1 millivolts, what I saw, I think maybe. What sort of 1 volt range? Yeah, I don't know. There is some life in this thing. It seems like when it switches ranges, sometimes it will come up. Like then. Maybe, I don't know. It's yeah. So you get 200 millivolts in that range, DC. Anyway, so it's still no output, but the oscillator started oscillating. take that off. Does it still oscillate if I take that off? It stops. So is it just noise? So if I have this clip on there, I'm getting something coming through the oscillator circuit. So something's working from that point onwards at least. If I look at it again from over here, look in TP3, TP4 starting to do something. I can see some ripple in that line. And again. So that might help me to determine what's going on actually. But anyway, I've eliminated all the FETs. So all the FETs are good, they're all switching. And that's the purpose of what that was for. Oh, so I thought whilst I'm getting some oscillation out of this thing, I can test some of the circuitry. Right, so I know I was getting a frequency at TP7, which is the output. This is at TP5, which is before the output. This is where's TP5? That's at the output of the quadrature amplifier. So that's before the input to the oscillator amplifier. So it's before the actual final one. So I hope you can actually hear what I said then. It's probably a bit noisy. So at this point here you can see oscillation there. I'm getting 3.6 megahertz oscillation with this particular setup, right? And that's at what are we getting? 370 millivolts RMS just there. If I come back over to the output, I'm getting the same frequency at 1.83 volts. Right, 9.9 volts, right? It must have been overscale. So the amplifier section is working. Right, I verified another part. So that's, and I've got nothing else connected. I mean, this is the other end of the probe right there. Right. It's obviously just a ground loop thing between the earth connections, which is making it oscillate. So instead of me having to inject an oscillator signal, it's done it himself, which is quite convenient, I suppose. So what I verified, get a drawing, is that's where I was getting the output there, and this is where I was getting the lower signal here. So between here and here it is amplifying, which means this bit is working. Awesome. Okay, the next little thing I'm doing here is I'm injecting a 100 kilohertz 100 millivolt signal from my signal generator into TP2. Now the reason I'm doing that is I'm trying to get the oscillator circuit to work, right? By injecting my own oscillation at the beginning of the circuit to close the loop, right? And what I'm trying to test is that the oscillator circuit will work all the way through. Now I'm injecting a TP2, which is at the input of the summing amplifier. So if I go back a page, that's that page there, it's represented as a little circuit there. So I'm injecting a TP2, which is right here, and I'm getting 100 kilohertz out at the back. So this circuit here is oscillating through there. It's passing right through. If I change the frequency setting, you can see that the amplitude drops down, where it goes off of resonance. Right, so it is resonating. That's 100 kilohertz there. And if I change these, you can see it's dropping down. Right, it's mixing two frequencies together. You can actually see there's two frequencies there. And if I'm changing these in such a small amount, it's not really changing anything there. Right, but if I go, that's 90 kilohertz on the front panel, 100 kilohertz front panel, 110 on the front panel. Right, or if I do 110, we're going down, you see it's dropping it down, so it's going off resonance. So the frequency is resonating through this. It is actually resonating through here at 100 kilohertz when I've got it 100 kilohertz coming in at the front end. So I'm actually thinking that this board is working. Right, I'm injecting here, it's coming out there. That's working. So I don't think this oscillator board is the problem, right? Because it will oscillate. It will oscillate. So I'm not just amplifying what's coming through. I don't think. Let's just verify that. So there's there, right? So that's that there as well. What voltage levels that? that is 6 volts right there, IMS. So I'm only injecting 100 millivolts. So all I'm doing is revoking the unit to oscillate. So if I do 10 millivolts, oh sorry, it's 10 microvolts I'm shoving, that's not right. 10 millivolts, it's still oscillating. That is 340 millivolts coming at test point 4, test point 5, go test point 7, still the same, very low. Alright, I'll go here, see there's nothing measurable there. So it is amplifying and it is oscillating. You can see because it's being amplified at that point there, which means these are working. Alright, so it is being amplified between here and here. So if I measure at test point 4, so I'll figure out where that is. It's over there with my clip. The wire's getting a bit tangled up here. Test point 4 is right there. Getting nothing there, right? So at test point 4 there's no signal, so this is definitely amplifying. Quadrature amplifier, check. Right, so now let's verifying the very first stage amplifier, which is the summing amplifier. So I'm injecting a 50 millivolts signal in TP2 and I'm measuring at TP3 a 2 volt signal, so it is definitely amplifying. If I change this level here, say 100 millivolts, here it jumps up to 5 volts. So proportionally it's also a lot greater. It's double the size, so it is doing quite a lot. What's the amplifier gain then? Let's go 50 again, so that's 2 volts, that's 40 times gain. Is that right? 4, 2, yeah, 40 times gain. That's what that amplifier is running at. Do 10 millivolts, I get 400 millivolts out. So yeah, about 40 times gain. So that all seems fine, doesn't it? I might just really look at that gain values on the other stages. So we got what's the next stage? Because all the amplifiers are the same. So I want TP4 and TP5. So TP5 is the output, which is over there. So I'll click this. So there's TP5. And so, and TP4 is the input, which is over here. And I'm seeing 400 millivolts here as well. So if I increase this to 100 millivolts, so I'm getting like 5 volts there. So we'll try and get a measurable amount. So yeah, that's also 40 times gain. That's what it should be. Okay, so I'm getting 800 millivolts out, I'm putting 20 in, 40 times gain, because all 3 stages are exactly the same. They're exactly the same attributes of each other. So each one should work the same way. So now I'll look at the next one just to verify its gain rating. So I want TP6 and TP7. TP6 and TP7, so it's TP7 right there. Hopefully it's not blocking the view of the scope too much. I'm trying to keep the noise down a bit. And TP6 on the input, which is, I've lost it, TP6 right there. So I've got 20 millivolts going in, 750 or so coming out. So all very similar. If I increase this to 100 millivolts, should go to 5 volts, pretty much. Yep, there we go. So all 3 amplifier stages are working correctly. So if I show you this, so all 3 are working correctly. They're all doing about 40 times gain. So it eliminates that part, and that part. All working. As you can see, these are the actual amplifiers here, there, and there. Each one, I don't know, I actually did 3 versions of the same thing, but I suppose because the part numbers different. But they're all exactly the same circuit, identical to each other. So far this board is looking pretty good. I haven't actually found any faults on it. Yeah. I'm going to keep looking. I want to make sure I'm very thorough and cover absolutely everything. But that works. Those work. There's not much else to go wrong on here. So this board might be okay. Alright, so after reviewing the circuit diagram for this board, I actually think I can eliminate this board as a problem. I believe this board is okay. So I shall make this one video, and this video will be about analysing the oscillator board, and that's what I've been doing, as you've seen. So I think I've eliminated this board. I think everything is okay on it. From what I can tell, it's alright. I think I already replaced those 2 caps there. I'm pretty sure I replaced those. I don't remember now. I'm pretty sure I did those 2. But anyway, the board looks like it's working okay, so I think this one's good. So remember to subscribe and give us a thumbs up. Definitely give us a thumbs up and like the video. Tell your friends, spread it. Spread the room, the links to this video and that sort of stuff, and post it in forums if someone's asking about troubleshooting one of these 5200As, and help to spread the word about it. And hopefully this will help somebody else at the same time. I'm still looking for more Patreons, as it always will be, to help support the channel and help to fund things. For me to buy bits of test gear like this to make these videos, I need to buy them. Right? I have to spend the money, and this isn't a cheap piece of gear. This is $1,000 worth of test gear, which I may or may not be able to fix. All right. So $1,000 New Zealand, that is. About 500 US or so they tend to go for, maybe a bit more depending on condition. But it's an expensive hobby, buying bits of test gear to try and fix it to do videos. So I really appreciate if anyone can spare $1 a month, $5 a month, whatever. Then go to my Patreon account and sign up to that and donate to my channel and help me to provide bits of test gear to do videos with, okay, or parts or whatever I have to do. Right, it gets expensive, this hobby. So please do that. If you are a $5 subscriber, you get a pre-release of most of my videos, not all of them, but the more interesting ones like this I've done on pre-release. I'll release them to the Patreons first, and then I will release them to the public a period of time after that. So that's what the $5 a month will get you. It's a pre-release if you like stuff quickly. You can't wait, and like me. So yeah, please do have a look at the Patreon and help support me, because I was really appreciate it. I could really use the money, because this is an expensive hobby. I don't make very little money from YouTube, nowhere near as much as I need to make from it to buy lots of gear and to do these kinds of things, because generally what I buy are things I'd like to keep. I rarely buy something I'm going to sell. So this I purchased because I want an AC calibrator, right? So that's why I bought this, like the other bits of gear I've bought as well in the past. So I don't make any money from reselling them, because that's not what I'm doing. Occasionally I will be, but usually not. So yeah, so give us a thumbs up and subscribe and all the other stuff, as I said before, and please check out the Patreon and support the channel. And thank you to my existing Patreon supporters. You're much appreciated. You truly are. Thank you very much. Catch you later. Bye.